welcome to my presentation on earthquake prediction on the North Anatolian Fault. To start with, I would like to introduce you to the city of Izmit, which in 1999 suffered from a magnitude 7.4 earthquake. This resulted in 17,000 deaths and 250,000 people became homeless. What's interesting about this earthquake though is that 2 years prior to this, Stein et al. Predicted a 12% probability for a magnitude 6.7 or greater earthquake to strike south of Izmit within the next 30 years. But what does this have to do with structural geology? Well, I would like to look at where will the next earthquake be on the North Anatolian Fault. To do this, I'm going to be looking at the tectonic setting, earthquake prediction, consequences of the Izmit earthquake, and some future predictions. So a bit about the background. The North Anatolian Fault is a 1200 metre long dextral strike slip fault, separating the Eurasian plate in the north from the Anatolian plate in the south. It formed around 13 to 11 million years ago, reaching the Sea of Marmara just here, only around 200,000 years ago. This is the area we're going to be focusing on today. These dots here are measurements of local seismicity from some different studies, and when adding the seismicity measurements to deformation measurements, Lang et al. 2019 found that the fault was locked to at least 3 kilometres depth, meaning that it's currently accumulating strain. With a dextral motion of 23 to 24 millimetres across the Sea of Marmara, this seismic gap may have accumulated a slip deficit of more than 5 metres since its last earthquake in 1766. Additionally, since the 17th century, the North Anatolian Fault has displayed cycles of seismic behaviour which starts in the east of the fault and moved westward. As we can see, since 1939, a series of earthquakes progressing westward along the fault have occurred, the latest being the two 1999 earthquakes just here. Strain and rheology are some more important factors to consider when it comes to the North Anatolian Fault. In Hussein et al. 2018, they used synthetic aperture radar images from satellite data to find average line of sight velocities. These are calculated using the Doppler effect, where a redshift is a positive velocity which is moving east in this case, and a blue shift is a negative velocity which is moving west, as we can see in this image here. As we can see by plotting this, there is a clear north-south gradient and east-west velocity across the fault. This is expected due to the dextral motion of the fault. From geodesic measurements, they found that the strain accumulation rate was constant for the entire 250-year interseismic period, other than the 10 years following the earthquake, as we can see in the second figure just here. This top figure shows the shear strain rates, which are calculated using estimates of locking depth and slip rates, plotted against the time since the last earthquake. The bottom figure is just a zoomed in version of this, where we can see that after around 10 years, a strain rate of negative 0.3 microstrain per year becomes constant. In terms of rheology, we can use the viscoelastic Maxwell model, in which strain rate is controlled by viscosity. Hussein argued that the rheology of the fault controls the temporal decay of post-seismic deformation, whereas the rheology of the substrate, which is away from the fault, controls the long-term interseismic strain. This means that the fault zone must be embedded in a strong lower crust, which is the substrate rather than the rheology of the fault itself, with a viscosity of more than about 10 to the power of 20 Pascal per second. However, because in this study they used geodetic observations measured over a few decades to estimate strain over centuries, it can become difficult to interpret their level of accuracy. Now that we understand a bit about the background of the fault, going back to 1997, Stein et al. Produced a paper detailing how they were able to analyse surface slip and fault geometry to map the transfer of stress in the fault. From this, they were able to calculate Coulomb failure stress change, which is given by equation 1 just here. This, of course, is the Coulomb failure stress change. Tau beta is the shear stress on the failure plane beta. Sigma dashed beta is the effective normal stress, and mu dashed is the apparent coefficient of friction. When the Coulomb failure stress rises, failure is facilitated on the plane. The Coulomb failure stress change caused by large earthquakes was then mapped out as seen in this diagram just here. We can see that for all earthquakes except for 1943, the next earthquake's epicenter was located in an area where the stress rose significantly, usually by about 2 to 5 bars. So taking the 1944 earthquake for example, the earthquake occurred just about here, and the stress transferred to this area just here, and then the next large earthquake was 1957, and that's where that occurred. Following on from this, they were able to begin calculating probabilities for the occurrence of earthquakes. To do this, we can use two models, the Poisson model and the conditional probability model. The Poisson model is seen here in equation 2, and it's a stationary model which assumes the probability of an earthquake within a time interval is independent of the time elapsed since the last event. R is a constant occurrence rate for earthquakes on that segment, N is the expected number of events, and delta T is of course the time interval T. With conditional probability, however, probability can increase with time. This means it can represent increasing stress in the fault as time goes on. And we can see this here in equation 3, where we can find the probability by finding the inverse derivative of the function of t evaluated from t to t plus delta t. The function of t being equation 4 just here, where m is the median recurrence time and s is the standard deviation of the recurrence time. By putting this together with the data from modelling Coulomb failure stress change, they were then able to predict a 12% probability of a rupture south of Izmit within the next 30 years following 1997. And of course, in 1989, the earthquake struck. So what happened after the earthquake? In 2020, Morozov et al. Modelled the state of stress and strain in order to understand what happened around Izmit after the earthquake. In the model, relationships connecting stress and strain were assumed to have averaged over the layer thickness by using this equation here in equation 1 to model generalized plane stress. From this, they then assigned an external stress field using geophysical data and analysed maps of the integral stresses, which are just here, as well as the stress intensity, which is equal to equation 2. The stress intensity is basically the energy content in a fragment of the geologic medium. These values of the stress intensity can then be used to interpret the state of stress and strain resulting from the earthquake. This map here shows the stress intensity difference from before and after the earthquake. This little star in the middle here is the epicenter, circles are aftershocks, and the lines are all faults. In areas where there's been an increase in stress intensity, such as orange area here and the yellow area here, we can see there's lots of clusters of aftershocks. We can also see that the epicenter, which is just here, which would have originally been in a very high area of stress intensity, thus causing the earthquake, is actually in a blue coloured area, indicating a drop in stress intensity. This is of course because the stress is being released once the earthquake occurs. So we also see there's the largest increase in stress intensity in this area here, which just so happens to be really close to Istanbul, which for reference is located 40 degrees 59 minutes north and 29 degrees 1 minute east, so just around underneath the number 2 here. So in conclusion, where will the next earthquake be? In 2004, Parsons calculated a Poisson probability of 38% that a magnitude of greater than or equal to 7 earthquake would affect Istanbul in the next 30 years. When incorporating the stress transfer, this rose to a probability of 53% plus or minus 18%. Looking further into this part of the fault, Bonov et al. Studied the seismic gap under Istanbul using microearthquakes. To do this, they recorded 835 microearthquakes over 4 years, and similar to Lang et al., which we discussed earlier, also found there is a 30 km long, 10 km deep seismically quiet patch on the Princess Island segment, which is just under Istanbul, as we can see in this image here. That's 10 km deep and 30 km wide. To explain this, there are currently 2 end-member hypotheses. One, that the slip along the segment is a seismic creep, or 2, that the segment is completely locked. Comparing this to historical records, which show an earthquake in 1509 and 1766 on the segment, it shows a recurrence interval of about 200 to 250 years, which is correct for it being about now, as well as similar faults such as segments of the San Andreas fault. They found the fault was more likely to be locked than to be aseismically creeping. This means that the fault is currently not slipping due to frictional resistance in the fault being greater than the shear stress in the fault, causing it to essentially be stuck. This makes the Princess Island segment of the fault the most likely nucleation point for an earthquake, posing a great risk to Istanbul and its 15 million citizens. In summary, the North Anatolian Fault is a dextral strike-slip fault featuring seismic cycling. The Izmit earthquake was predicted using Coulomb failure stress change and probability calculations. After the earthquake, stress rose underneath the locked segment at Princess Island under Istanbul, which is estimated to rupture by 2034. These are the references that I've used. Thank you for listening, and I hope you enjoyed.